Engine Performance Expo viewers. We're still here at Jasper Engines and Transmissions in Jasper, Indiana. This lab here is pretty cool, guys.
There's some great toys here.
There's a lot of really great toys here.
Yeah.
But one of them behind us, behind Chuck here, is, you know, a profilometer, which we've seen these a lot.
Sure.
But there's something different about this one versus the one we're dragging around, putting in cylinder bores all the time. So, Mark, explain the difference between what this one is versus the one we normally are using.
Sure. This is a skidless device. So the only thing that touches the surface is the diamond.
Right.
There's no little skid holding it in range.
Right.
So it's suspended by its own drive unit, which is essentially perfectly straight. So we're going to touch the surface with a diamond and pull it along a straight line without any help.
All right. And what's the significance of that?
The significance is we can see waviness now.
Right.
If we think about our skidded gauge, the skid holds the stylus in range. And if the surface has a hump, the skid goes up and we don't know it.
Right.
But this one, it's just the diamond.
Okay. So, Chuck, why is that so important for what you have sitting behind you here?
So, the surface of a cylinder head, we want to be as flat as possible to apply a uniform amount of clamping force to the gasket, right? With modern gaskets, MLS gaskets particularly, and they're used in from heavy-duty diesel to high performance, right? So they're used everywhere now. In the past, you know, it was a limited breadth of products that they went on, but today they're everywhere. Well, if I have a wavy surface, it's kind of like the suspension bridge thing. You know, suspension bridge sags, but I have a pretty rigid gasket that doesn't really sag, and it doesn't fill those voids.
Sure.
So now we have either combustion leakage or coolant leakage or oil leakage.
None of which are good things, by the way.
Right. Look at the complexity of heads to now. You know, they're all the brains and controls are in the cylinder heads. So now we have high pressure lubrication up there, the coolant, of course, potentially a fuel rail that's running through. So we can have mixing of materials, but the biggest thing is, you know, is combustion escaping and getting into your coolant, your fuel, your oil. So that's all bad. So the flatter the surface, the more engagement we have, and the better for sealing the engine. MLS gaskets are also hard to read. Old conventional gaskets, when you see things like that, it usually removed the facing material from the body or the core of the gasket, and you could see exactly what happened. Now we get a gasket back and we scratch our head, we take a straight edge and check it for flatness, and oh, it's okay, you know, you know, it wasn't 3,000s warped or whatever, because you'll look in a service manual and say maximum warpage 3,000s. Well, uniformly across the surface, that might be acceptable, but usually it's much higher frequency, so we have that deviation in a very short area. So it actually, if you take MLS gaskets and kind of pull the layers apart, is where you're going to see the indication of compression, leakage, and things of that nature. So waviness is much more important than ever before in what we're doing.
So you raise a really good point. You know, you talk about warpage and that big scale flatness. Gaskets like that. I mean, that's what they're made for, is to bend to big scales. If I tried to cram a stack of paper between my fingers like this, it'll fit. But the same depth like this, they won't fit. So is that flatness of 3 thou over the whole surface or localized? And
back to the frequency you were just saying. That's what matters.
Right. So in some places what we do is we have flatness, but we also have zonal flatness. You're allowed 3 thou over the whole surface, but only 1 thou within 2 inches.
Right.
Okay. So that's the difference here, is that surface finish does matter. Like roughness matters.
Yes.
In terms of having everything clamped together and fixated right. But really that next level you have to look at, which is obviously maybe even more critical, is the waviness. And that waviness can be imparted by the tool you're using, correct?
Right, and actually we've been having conversation with the team here about what induces some of that waviness.
Sure.
Now, you always start with the easiest thing first, right?
Okay.
So if I'm seeing waviness, the first thing I'm going to do is make sure that all the feet are secure on the floor. That's the easiest thing to do. Okay,
the machine's not rocking.
Is the machine level and secure to the floor? And then I go to my fixturing that I'm going to put my part on, cylinder head, cylinder block, and make sure that that's all rigid, that I have good integrity, that I can tie the part down, and that's not inducing waviness. And then you can start to look at things like ball screws, motors. One of the things that was brought up was actually a drive issue. So intermittently, the motor was stopping. So there's in the CNC world, vertical machining centers or lathes or whatever, they have ball bar testing. And ball bars you fix into the spindle, and they're fixtured on the machine somewhere. And you tell your machine to do something, and it does what it thinks it's doing, and this thing qualifies what it's really doing.
Right.
And what happens when motors are going different directions? Okay, so I'm going to run X positive and change my mind and go X minus,
Yep.
Y positive, Y minus, Z positive, Z minus. And you have what we call reversion spikes when it gets to those points, and you can adjust a lash out with that. So basically, that's what they were actually seeing is, okay, it gets to a point, the motor is intermittently start, stop. And so as it starts and stops, once you come up to that particular frequency, it probably settles out. But in between there, I might be setting up the opportunity for vibration.
Sure.
And
that
it's
vibration turns into waviness.
Right. So
That only makes
there's
sense.
a lot of places you can look. One of the things from my past was like there's holes that are milled in the tool holders.
Right.
Well, we use some lubricant and we spray on the head surface, and that makes things sticky, and we create chips, and now they're up inside the fly cutter head. Now it's out of balance. So we talk about balance often.
Oh, yes.
That's a really easy
Wow,
place
that's a
to
great
just
point to think
take
about.
some carb cleaner and wash that out, and all of a sudden, a problem that was there 30 seconds ago just went away.
Your fly cutter's out, literally it could be out of balance, just a buildup of gunk,
Yeah.
and now it's inducing waviness because it's sitting there floating, essentially.
Exactly. So, that just emphasizes how important maintenance is.
Yeah.
Because we need to maintain it as we go, not let it get to chaos, because that chaos can end up in the surface. And
Okay, so what is this example back here? Explain what we have back here, because I know this is a cylinder head, obviously, and I can see lots of machining marks on there, but I also see Mark's graph over there. And is that good? Is this bad? What am I looking at here?
let's let Mark elaborate on it.
Sure. Well, in this world now, we're a skidless measurement. This is really important. This is the cross section of that metal.
Got it.
So this is exactly everything. If you were to take a microscopic walk, not just looking at the fuzz, but looking at the lumps, or not just the grass, but the hills.
Yep.
And so here's a graph from this surface. Now we took this measurement in a particular location where we could see some lines on the surface.
Yep.
And those lines are very visible to our eye.
They look ugly.
They look ugly. There are 3 lines that look like there's a problem.
That's like, this shouldn't be there. This has got to be a problem. And it's next to a water hole, too, by the way, so it's even equally scarier.
Equally scary, right.
Yeah.
So those lines might cause us an alert. Like, if the whole surface was covered with that, we'd be scared. But if we check out the profile graph itself, it was just a little frostiness in the bottoms of the valleys that light up to our eyes as this horrible thing. Our eyes only see slopes. They don't see height.
Okay.
The eye sees a change in reflection. In those areas, the surface doesn't reflect as well. But you see when we zoom in over here, the bottoms of the valleys are a little rougher in a spot here and then here and over here. But the texture is the same, really, in terms of roughness.
Okay.
The gasket is going to see the same roughness throughout. So that was one interesting piece right here. The other thing that I tend to look for in a data set like this is what is dominant. What's the shape that really is going to get me? In this graph, the red line is the waviness, and everything above and below waviness is roughness.
Got it.
So imagine if we flatten that out, that's the roughness.
Got it.
But if I look at this, I say, what should I be controlling? Should I be controlling the cutting action or the wobble of the mill? Well, the cutting action seems to dominate this data. I would say there's not a lot of waviness compared to the roughness in this example.
Okay.
Let's switch it around so you can see what I mean. I'm going to load a data set right here on the same scale. Now check out that.
Oh, that looks really bad.
Right. So now
That's like a sawtooth.
Yes. Now the waviness is totally dominating the roughness. If we look at the red lumps compared to the fuzz that lives on top of them, this is a real waviness deal. Now this particular data set was a mill head that wasn't square to the axis.
Got
it was
it.
wobbling once per revolution, and you can see that sine wave wobble going on. So squareness was a waviness cause here.
Okay.
Each revolution wobbled back and forth. So in this case, managing waviness would be really, really important. Imagine an MLS gasket trying to, find a home on
You
that.
can't find that, right? Yeah.
Right.
Right.
And
can you go back to the previous?
absolutely.
So this indication here is where the gasket manufacturers do have a plan for this. They have what we call cold seal technology that they'll apply to the gaskets, and they can deal with that type of stuff. There's nothing they can do to deal with that previous example.
The
That's
big
a
one.
failure.
Right.
That's a failure.
Yes, exactly. So it's a matter of balancing enough roughness to give us some traction, kind of grip in there a little bit.
Bite.
A little bite, but keeping waviness under control to manage conformability. We can conform to certain frequencies, shapes, and in this case, we should be able to conform well because those wavy lumps are within the zone of roughness. And if that roughness is acceptable, that waviness should be acceptable.
This is too cool. This is why I hang out with these guys in places like this, because you learn something every time. It's go back to the one that's really scary looking. Because
right.
I just want to see it one more time. Like, yeah,
You want to get scared?
I just want to see it. I want, yeah, that is really, really horrendous, by the way. But that's why we have these tools, right?
Exactly.
Right.
And how does it present itself in an engine? Again, if you're looking at the gasket itself, you might see the layers if you pull the gasket apart. Or let's take a look at a Fuji impression.
Yeah.
This is
So,
fun.
bright red, high load. Pink, low load.
White,
White.
White, yeah.
Time to take it apart.
no load.
So there's some really, really great tools out
You
there.
can see a ton of variation here, which is really amazing. That look at that. It's really red near the the studs,
The bolts.
the bolts.
And as we talked about earlier, and that's pretty standard. The
clamping force.
11 millimeter bolt holes that we were looking at as far as clamp force, they're pretty much, you can say they're going to be 12 to 15,000 pounds of clamp force. That's
Right.
just. I've looked at bolts for years and years, and that's what you see. So the material, the strength of the gasket's got to be able to stand up to that as well.
Yeah.
But
So you introduced an interesting point on those holes. I want to go back over here a minute if we can.
Okay, sure.
So remember the defects we just pointed out, and you rightly observed they're coming out of a hole. Think about that cutter dynamic.
Oh, intermittent cut.
Intermittent cut, exactly. So we come out of a hole. Now, sometimes maybe on the block side, we'll have a tab over here or something like that. Totally intermittent. And we can actually see it set up waves. Depending on when it hit,
It starts to
might go
bounce.
low one revolution, the next revolution it's high, the next revolution it's low, based on the width of the cut changing. And we can introduce waviness
To the intermittent cut.
because the intermittent cut and the variation in thickness coming out of it. So
It's like your spintron then for that. It's like, am I in valve bounce? Yeah, I'm in cutter bounce.
right.
and even unsupported low. Let's say there's a tab out here on the block. It's not supported, so it's not going to cut. It bends down and springs back when you're done. And that also can contribute to waviness based on springiness.
Right.
So there's a good technical term for you.
Springiness.
Springiness.
New word.
It's like winteriness, only it's warmer.
Like slickeriness.
Slick, you got it.
Yeah.
And we've talked about this in the cylinder bore surface finish. If you're not measuring, you're guessing, because more so today than ever, I have plasma wire transferred for the cylinder, or I have alusil, Nicosil, compacted graphite, typical just gray iron, and it's a real challenge to say what's going to work and how it's going to respond. Like the CGI stuff is like machining steel; it reacts much like steel. So tool geometry, speeds, feeds, you need a library of everything that I've got going through my shop, and keep track of it. There's not a one solution fits all.
Sure.
But that's the great thing about what we're doing here with Engine Performance Expo is we're giving people this network of resources so that you don't have to be intimidated by all the variables. It's as long as you know that they exist,
Right.
and then you've got resources to be able to pull to action to be able to make sure that you solve the problem. That's what it's all about, is that we're smarter collectively than we are individually.
Absolutely.
Right.
You know, the networking part of it. You know the names, you know how to get a hold of the people, and we can get solutions because someone has dealt with it already.
Yeah.
It's an old industry.
Sure. Right.
And even the modern stuff, you know, we've been talking about honing cylinders with CBN and diamond. And you take a look at like the two-stroke Detroits in the 80s, they were honing the cylinders, induction hardened cylinders with CBN. So it is making its way out into more segments of the market. But again, just, you know, rely on the opportunities to talk with the people that are in the group and a part of all these teams, and we can get to the solution.
Sure.
So the moral of the story is change is happening. It doesn't have to be scary because you have friends that can help you.
What a day, what a day, what a day. Yeah, my brain is swollen. I've learned so much today. They told us, don't start cars. We are not going to listen.